In this video, we're going to look at solutions of the plane wave equation, what form these solutions take, and this will lead us on to the idea of characteristics as being a form of solution of the wave equation. So here is the wave equation. d2s dt squared is c squared d2s dx squared. The general form of solution of the wave equation is of this form here. So if we're looking at s being the displacement of particles in the gas as a wave travels through them, then we have some function f1 of x minus ct and some function x2 of x plus ct. What we're going to do now is have a look at each of these in order. So we'll first look at this first part of the solution, f1 of x minus ct. Say we have a displacement that's plotted vertically as a function of distance along the gas through which this wave is travelling. And let's say that at time t equals 0, the displacement has this shape shown here. So at time t equals 0, c times t goes to 0, and this is what the shape of f1 will look like as a function of x. As a solution of the wave equation, if we look at some time later, say t equals t1, then the shape of the wave is the same, so it's still got this shape here, but it's displaced in space. The x amount that it's displaced is going to be c times t. And if t equals 1, then it's displaced a distance c. So if the level of f1 at x equals a at time 0 is this level here, say f of a, then the function will have the same magnitude at position x equals a plus c at time t equals 1. Similarly, at a later time, say t equals 2, it has the same shape again, but it's displaced further. In this case, a plus 2c will be that same value, f1 of a. So the physical significance of this part of the solution of the plane wave equation is that this first term is a wave of constant character running from left to right at a constant velocity c. If we look at the other part of the function, f2 of x plus ct, then we get a similar story. But in this case, instead of the wave travelling to the right, the wave travels in the negative x direction. So if this is our shape at time t equals 0, as we had before, and this is the value at a at position x equals a, this is the value of that function at time 0, then at time t1 it's displaced by a minus c, and at t2 it's displaced by a minus 2c. So the physical significance of the second term is a wave of constant character running from right to left at velocity c. This leads us onto the idea of characteristics. So there's our solution of the wave equation. If we plot x and t and we look at our character of the function, then we can line up any point on the function and we get this characteristic line running up in the xt diagram to the right. Similarly, for the left running wave, if we plot points of constant character, then this line is travelling up here at an angle going out to the left. And these lines are referred to as characteristics of the solution, characteristic lines of the solution. So xt diagrams are quite useful for looking at these characteristics. And what we can say is that this line is a forward characteristic, x minus ct is a constant, and f1 is a constant along that characteristic, and this is the backward running characteristic, x plus ct is a constant, and f2 is constant along that line. So characteristics are useful for illustrating wave interactions and tracking wave histories. We use xt diagrams in other areas of engineering and mathematics. An example is in shock tubes, which I'm familiar with. So a shock tube consists of a tube which has got a high pressure gas in one end, separated usually by a diaphragm, to a low pressure gas in another part of the tube. And we remove the diaphragm, or we rupture the diaphragm, and that causes a shock wave to travel down through the shock tube and reflect from the end, and then we use that high pressure, high temperature gas to feed a nozzle, and we can put a model in a test section to look at flow over a model. So here's an animation of what happens when this diaphragm ruptures. At the top is a Schlieren effect, which shows the effect where density gradients are in the flow, and at the bottom is the concentration of the gas. So the blue is the gas which was initially in the driver, and the yellow is the gas that was initially in the shock tube. And what we see when the diaphragm ruptures is that a shock wave forms and starts running down the shock tube, and the contact surface is the interface between the expanded driver gas and the compressed shock tube gas. And upstream of the diaphragm we see expansion travelling back upstream there. And if we go to the end of the shock tube, then we see this shock wave travelling down, which reflects off the end and comes back and hits this expanded driver gas and passes through it, and we bring most of this gas to rest, and then eventually that gas expands out through the nozzle and flows out over our model. So we can represent this on an XT diagram. So this is distance along the tube horizontally, and this is time vertically. In this case our tube is about 4 meters long, and we're looking at milliseconds of time, so that's up to 5 milliseconds. And if we look at contours of density within the flow, we can actually see this shock wave travelling down the shock tube and reflecting off the end, and this other line here is the interface between the expanded driver gas and the shock tube gas following down behind it, and when that shock wave interacts with that contact surface between the expanded driver gas and the shock tube, it essentially brings it to rest, and we have this gas in here at condition 5 which is feeding our nozzle. So this XT diagram is a useful representation in various areas of engineering.